and make that screen wide. So I'm adopting a fairly conversational, intuitive approach to explaining UML. And the first thing I want to stress is the importance of modeling, the importance of knowing how to model a situation or a process or whatever it is. And I just want us to come to some mutual understanding of what a model is. So for this session, in week 5, halfway through the course, hopefully we can come to understand and recognize the need for abstraction in modeling and the huge importance of the value of being able to abstract successfully. And in addition, I'm hoping that we come to an understanding of the context in which UML can be used and was developed. And the first question to you is, first obvious question is, what exactly is a model? So what do you think what do you think a model is? I mean, I've got some suggestions and some ideas, or rather some examples. And I'm thinking of models of trains, maybe using toy trains and toy tracks and operating these trains by electric motor and so on and so on. Or you could, there's a different kind of model. It's a model of molecular change during short periods of time. I mean, how molecules evolve and change. Or maybe a completely different kind of model would be a model of the Big Bang event in the universe. And I guess you'd probably do that, not visually, but mathematically. Or maybe you're interested in citing the example of a model of Kew Garden. I don't know whether you've ever been to Kew Garden.
No.
It's quite an interesting place to visit.
Sorry.
And or maybe you could cite as an example a lift system with distributed control. I mean, maybe what I've got in mind is a system with 25 different lifts and serving a large number of people in a very, very tall skyscraper using distributed control. Maybe I'm going to have a separate controller for each lift, and they're talking to the master controller, which is just instructing them what to do, or if there's any kind of problem, it's going to resolve the problem. So here's a first shot. The model is simply, or should I say simply, a model is a simplification of reality. And then the question is, well, if you're simplifying a concept of reality or something real, does that always entail abstraction? And the question is, what is abstraction precisely? What is abstraction? Well, I guess a very naive description of what abstraction is that you're just peeling away unnecessary detail. You're aiming at key facts and structure, and everything else is unimportant. So I don't know whether you could come to agree with that, or maybe you prefer to say that a model is simply a blueprint of a system.
Exactly, I was literally going to use that word.
Okay.
Blueprint or a plan, yeah.
Yeah, okay, or a plan, or simply a concept, an abstract concept of something you want to construct or build. So I think any of those are okay. I mean, I've actually cited a phrase that I picked up from a document discussing abstraction in software, and it semantically closed abstraction of the system. So I'm not quite sure what that means, and maybe it's something we could think about. So the question now is, why on earth do we naturally make models? Or better question is, why should we make models if we're in the business of constructing something? I mean, maybe, I've got a 3-hectare garden and I want to redesign it. I mean, surely, it strikes me, it's obvious that we should plan it, or, construct a model of what I want the garden to look like. Okay. So, but one set of reasons for answering that question is, why do we make models? Is, first of all, to communicate structure and behavior of a software system. But if I wanted to tell you how my lift system, what my system is going to do, surely I should perhaps give you or describe a model in which you could come to better understand not only the structure of the lift system, or the intended structure of the lift system, but its behavior. I mean, how does it behave? Well, I'm going to tell you in the model. It's going to be very clear. Well, secondly, to visualize and control a system's architecture. I mean, that's quite important. It's important for me to have some kind of overall idea of what the system's going to look like, and that's what I mean to visualize and to control it. Have I got an architecture in which I can play around, I can alter components? Maybe I want to change component A of the architecture to component B because I think B is better. Thirdly, and I think this is very important, to assist in understanding a system under development, so as to enable us to actually reason about and analyze a system and criticize a system if we've modeled it. We might instantly see that there's some kind of flaw that we can do something about. We can change that, or maybe given a model that will enable me to fully analyze the system. Like, I can say, well, what happens if such and so events? Will the system under development be able to handle them? But I guess a fourth possibility is that it exposes the opportunity or opportunities for simplification and reuse. If I'm modeling something, I'm actually have simplified a system, and maybe the simplified system is perfectly adequate for the purposes that I'm building it for. You have to reflect on these possibilities. I can model a system in order to manage risk. Again, if I've got a model, perhaps that's going to enable me to grasp the risks of bad things happening. And I guess finally, a model enables me in a very convenient form to document or record decisions. If I've got a model and I change it, I can easily document that change. And I think that's very important, because someone in the future might come along and wonder why I've actually got feature F as opposed to the original feature E. And maybe the documentation can include the reason why that further component was included. And from I guess the construction industry, in terms of architecture in that field, there always are two important sets of documents for building a particular design. First of all, you've got the drawings, which give you two-dimensional representations of everything in the architecture. And secondly, the actual specification. And the specification actually tells me what is being shown, or what the objects shown are made of, and what the objects are, what their performance is supposed to be. I mean, it might be girders or a concrete floor, or I'm going to, in the specifications part, I'm actually going to specify the requirements of that material. In other words, how it's to be composed and so on. And so the drawings consist of elevations and floor plans and detailed drawings of maybe a portal or a patio or some steps. It'll give you a site map, and it'll give you a general drawing that involves all the other finer detailed drawings, so that you get an idea of what the overall building looks like on the one hand, and from the specification and the detailed drawings, you know exactly how to construct every single element of that particular architecture. So, you know, this idea of pictures of parts of building and specifications has actually been around for a couple of thousand years. So if you think about, you know, still going on about modelling and the simplification of reality, what ordinary cases of modelling come to mind? Well, maybe drawing a simple line to represent a proposed garden wall, or letting a variable A represent any number of maths. I mean, have you modelled anything recently? Can I ask you whether planning a journey from London... Sorry, I was going to make that personal. So, does planning a journey from one side of the room to the other involve any kind of modelling? If you had to build an android, I mean, I don't mean a mobile phone, but a man-like robot to perform the task, would modelling making a trip from A to B be involved? And I think probably in the past I've actually mentioned something called Occam's razor. Do you remember?
Yeah, you did in class.
Do you remember what I said about it and what's involved in that?
Yeah, it had something to do with having two different options / explanations to a certain scenario or event, and the simpler option being usually the one that's right.
Yeah.
The most logical option being the one that's most simple to explain.
Yeah, I mean, what Occam's razor state? Occam was a medieval English logician who's very famous for saying in Latin, "Do not multiply entities beyond necessity." In other words, keep things as simple as possible. No matter what you do, keep things simple. If you're going to travel to the Hindu Kush mountains, just take what you really do need, not your whole wardrobe, not 5 pairs of walking boots. Just, you know, take a helmet and some shorts and some mountain climbing boots. That's all you need to do. You know, don't add anything. So I guess Ludwig Wittgenstein became famous nearly 100 years ago now for proposing that sentences of language are, in fact, again, from a logical point of view, models of reality. I mean, whenever you utter a factual sentence, in a sense, they're giving you a logical picture, or giving the person you're talking to a logical picture of reality. And he's also, as we know, I think, he's famous for inventing truth tables. So what's the, you know, perhaps without hanging around for very long, let me ask the question of what is the practical and the theoretical importance of modelling? I mean, can we be a bit more? Well, modelling involves the proven and accepted engineering technique of using a divide and conquer principle. If I form a model of what absolutely must be a very complicated system by simplifying it as far as I possibly can into maybe a set of abstract components, I'm effectively dividing a problem involving a lot of design and analytical complexity into something that's much easier to solve. I mean, if I've split the original problem into 10 different parts ranging from A to whatever, it means that I can at some point start work on component A, then move to component B, rather than having to deal with a single block of complexity. We build models of complex systems because we cannot comprehend such a system completely in its entirety. So, and I'm thinking of Microsoft 10 operating system, which I think was it 100 million lines of code? And if you wanted to come to understand that, you probably will want to try and reverse engineer it and to simplify, to build a model and simplify it so that we can understand what each part of that code does. And if you looked at all the Redmond documentation of Windows 10, say, it's actually incredibly well documented, and it's presented in terms of a model consisting of sub-models, and I guess the operating system was very much designed in a top-down way rather than a bottom-up fashion. And I don't know why I've got this phrase here, need to build the right software correctly. That's something, a phrase from software engineering. It's not enough to build software, we've got to build the software that meets our requirements in a fully functional fashion. So we need to build the right software correctly. That's a bit of food for thought anyway. So two main modelling approaches in software. First of all, it's the functional, and it adopts a purely algorithmic perspective, building blocks of functions or procedures. And these sorts of systems are quite brittle in the sense that they're broken. And I don't want to expand on what I understand by a functional approach, but it means you're just going to start presenting algorithms to solve software problems. But on the object-oriented approach, you're just going to systematically use the right building blocks of classes and objects, and the names of the class are going to relate to the actual problem area that you want to solve. And I guess models are important in all engineering disciplines, whether it's aero engineering or space engineering or nano engineering, and so on. So when something is to be built, drawings are made that describe or depict the look and behaviour of the thing. And it could be a new Dyson vacuum cleaner, a pen, or a nano device, or a mode. And I guess what the scale of this is. I mean, this is actually a mote. It's an electronic device. I've mentioned motes before. And the size of this is actually this represented by this little object lying on top of, I think it's a dime piece. And so if I'm working on a completely new application, whether it be hardware or software, best if I start thinking pictorially as to the look of the system that I want to build. And I'm going to do that top down, like if it's a radio device such as a mote actually is. I'm going to design little subcomponents that actually implement particular needed, desired functionality or functional parts of the system. So, what am I saying there? I mean, during the work of making a model, I mean, it's a bit vague now because I've got no idea what the model is. I mean, let's say it's a model of a new kind of lift system. During the work of making a model designers need to investigate the actual requirements of the finished product, such as the functionality, appearance, the performance, the cost, the reliability, the technology of the actual thing. I mean, my stating that is really, to me, stating the absolute obvious. When you start making something, you've got to think about the requirements of what it is that you want to construct. And model designers must create a model that describes all the different aspects of the product. Why? Well, if you miss one of the aspects out, you're inviting disaster. And a model is often broken down into a number of views, each describing a specific aspect system under construction. And a short period of thinking about all this is that model creation is a creative activity, and there are hardly ever be justified in saying it's a final solution to the design problem. I mean, somebody could come along and redesign it completely or in part or improve your finished solution. And so it's a bit meaningless to talk about correct models or correct answers. So a picture, or maybe a logical picture-based model, pictorial model, is like the proverbial, like the old proverb, is worth 1,000 words in terms of explaining what it is, what the look of something is, or as indicating what this object pictures is capable of doing. So a picture doesn't have to be graphical. It can be class-based, which in a sense giving you an overall picture of a system. So the model provides a criterion for judging the quality of models. Does that make sense? But what are the useful criteria for judging the quality or fitness of purpose of models? Well, presumably a useful model is one that is accurate because it, like an architect's drawing, is going to accurately show what the building is going to look like. It's consistent So every perspective that you've modeled is actually consistent with one another. They're not going to conflict with one another. The model is easy to communicate. Look, I'm going to show you a model in a moment, and it's going to fail in its task if it fails to communicate what it is that I'm proposing or what I've built. You know, models should be easily changed, and I think I've already said this, easily understood. Or maybe I could simply say model is usable in all those ways. Like it's easily changed, easily understood, it's consistent and so on. Right, so I'm just going to mention the fact that one of the views of a model, one of the aspects of a system that we can develop is what's called the use case view. The use case view, and this is of critical importance since it drives the whole process. Right, and hopefully we're going to familiarise ourselves with some key UML terminology. So the universal modelling language's goals are simply to model systems using purely object-oriented concepts. In other words, if you use UML, in a sense, you've got to believe that you can describe or build a system using nothing other than objects and classes, nothing else. And we can couple. I'm going to leave this out because I'm not quite sure what the point is. Couple conceptual and executable artifacts. Address issues of scale and I've gone backwards, unfortunately. I'm sorry about that. I guess it was. And a modelling language is going to be created that can be used by both humans, i.e. the human designer, and machines. Machines can understand a UML model, for example. You could feed in a UML model into the right sort of machine, and the machine will be capable of building the object, which is a bit surprising. So, no single method or design process is actually implied by UML. Modeling language simply gives us the notation, symbols and rules for their use that enable models to be constructed. And all of the elements and diagrams of UML are based on the object-oriented paradigm. So what I'm really saying is that UML is going to consist of quite a large number of diagrams, different sorts of diagrams and elements that all are intimately related to the idea of an object-oriented world. So we're going to investigate that a little bit. UML can be used as a model for a broad range of systems, information systems, technical systems, embedded real-time systems, distributed systems, and systems software. I mean, it's quite a lot. Business systems. Difficult to believe, after you've actually seen a little of UML, it's used in all these sorts of different systems. Yeah. Right, so importantly, I'm indicating that 5 phases can always be distinguished in system development. The first of all is the requirements analysis. Yeah, well, we've mentioned the importance of getting the requirements accurately described. We need to analyse the real-life problem in order to derive a set of requirements. And UML uses, for this purpose, use cases. These allegedly capture system requirements. And in use case modeling, agents and actors who will interact with the system are going to be modeled together with the functionality required from the system, the use cases. Right? So the actors and use cases are modeled by means of use case diagrams. So I'm dying to see what a use case diagram looks like. And I hope you are too. And what a use case diagram shows is the relationships, holding, and communication associations between various elements. So each use case will also be described in text that specifies the customer requirements. Okay, so we've got this to look forward to, the derivation of requirements of system software using what are called use case diagrams, which are also accompanied by text that specifies the requirements. So secondly, the analysis phase. This phase involves the primary abstractions, the class and objects and mechanisms that are present in the problem domain. And here, classes that model these are identified along with their relationships to one another. And guess what? These are described in a second kind of diagram called the UML class diagram. Right? So hopefully all this will become clear in a very short while. So thirdly, collaboration between classes is indicated to perform the use case functionality. So in other words, we're starting off with a use case, a description of the requirements. We're going to analyze what's actually needed in the system in terms of classes and objects. And thirdly, we're going to explain the relationships between the classes in order to develop a credible implementation of functionality to bring about the customer requirements. So hopefully that makes a bit of sense. And in analysis, only classes that are in the problem domain are modeled. And we're going to defer detail. We're not going to look at detail. So we're going to keep everything abstract here. So in analysis, only the classes that are present in the problem domain are going to be modeled. So in the next stage, i.e. the design stage, here the results of analysis phase, the phase that we've just looked at, are expanded into a technical solution. And if needs be, new classes are going to be added to provide the right infrastructure. So we might need to use a couple of interfaces, a couple of databases, and so on. Right, so the problem domain, I mean, this is getting a bit boring. I'm sorry about this, but I want to document all this. The problem domain, the domain problem classes from analysis are built into the technical infrastructure. The results in detailed specifications. This results in detailed specifications for the construction or implementation phase. And I'm just skipping to one of the phases, the test phase. And there are lots of different sorts of tests that you can subject a system to. They're very, very important. And acceptance tests are conducted by the customer to verify that the system satisfies the original set of specifications that will have been shown the customer. And we actually, a system development will involve lots of different UML diagrams, and in each phase of software development will result in UML diagrams. And these UML diagrams will form the basis of test teams' work. So, for example, oops, let me go to the 27, 16, 17. For example, system tests will rely on use case diagrams to validate that the system behaves as originally defined by those diagrams. So, just pausing a little bit, UML can be used for a range of modeling tasks, all phases of development and for all types of systems, and general modeling of constructions that both have a static structure and dynamic behavior. I mean, by having a static structure, I mean maybe an object or set of objects that have state and you can change that state. And I'm comparing that with a much more complicated system like an air defense system that's monitoring the skies and responding to what's actually sensed in the skies by appropriate actions, or even our lift system. This has got a dynamic behavior. Shoots up to level 155, slows down, opens its doors, keeps the doors open, and so on. So, do I really need to go through all this here? I'll skip through this, talking about diagrams. These are the graphs describing the contents in a view. UML has 9 different diagram types, and my expectation is that you'll come to learn about 5 very important kinds of diagram in this in software development. Model elements, the concepts used in the diagrams are the model elements representing object-oriented concepts such as classes, objects, messengers between objects, and relationships between these concepts using association, dependency, and generalization. Element can be used in a variety of types of diagram that mean exactly the same thing. I mean, we'll come to grips. So here are the views. So there's different views involved in the development of a system. We're going to be interested in the use case view. And just to briefly explain each of these views or aspects, ways of looking at a system, or aspects of a system. So the use case view shows the functionality of the system. That's important. As perceived by external users of the system, the actors involved. Logical view is show how the functionality is designed inside the system and in terms of the static structure and dynamic behavior. So logical view, I guess, is looking at the classes that together are capable of creating the functionality required by the use case view. I'm going to skip out the concurrency view and the other view. So I'm going to just, this is where we really start. Use case view, details. So what I'm going to describe here is the intended functionality as perceived by actors, and the actor interacts with the system. I mean, it's like I could specify a use case of a doorway and a door by illustrating the fact that you, Mohammed, are the user of the doorway that allows you entry into your room. You interact with the system at that point. So I could actually give a use case, a typical use of your door and doorway. I mean, that's not terribly interesting, but it enables me to understand, properly described, by how a door is actually used, what the functionality of doorway is, and what you can do with the door. Okay, so I'm just repeating myself by saying that this view is absolutely important at its core, since its content drives a lot of the development of the other views. As I've already said, logical view is a description of how the system functioning is provided. And okay, so a lot of repetition here, but it's worth reading through, believe it or not. So let's take a look at some of the diagrams that I've been referring to. These are the graphics that show model element symbols arranged to show a particular part or aspect of the system. And the diagram is part of a specific view, for example, of a logical view. So here we are, the first diagram is the use case diagram. It defines what happens, what the system's capable of doing, without specifying how. How are you going to engineer a system to bring about the required behavior? It enables you to specify the desired behavior. And it promotes communication between the end users, the domain experts, the architectures, and the developers, information modelers, and so on. So here I've got this diagram. So the use is to process a loan. And it means that an actor such as Chris Kenberg is named can interact with this. It can actually start something up. This is what the system is capable of doing. Processing a loan. This is the use. This is the diagram. So at the moment it's a near vacuous, very stupidly simple illustration of what a system, it might be a computing system, or it might be a specific, very intelligent banking system that can actually enable you to input financial details and the process loan system to analyze everything and determine how much loan you're eligible for, or whether you're eligible for a loan, full stop. So a use case is a description of a set of sequences of actions that a system performs to yield an observable result of value to an actor. And this is an examinable definition of a use case. We'll see far more complicated use cases later on. The description of a set of sequences of actions that a system performs to yield an observable result of value to an actor. Okay, so it's something of value, something useful that the system is being depicted as capable of. But secondly, so different sort of diagram. A class in UML is a description of a set of objects that share the same attributes, operations, relationships, and semantics. So typically, a class diagram consists of a name, and in this case it's window. Got two variables, origin and size. And it's got two methods, two operations, open and close. I mean, maybe you could specify where the window is to be located and the size of the window, and you can do exactly one of two things on it. You can open it or close it. showing multiple diagrams. And here I've got a portfolio class. Again, it's going to be divided with operations and maybe some variables or some attributes. And I've got a trader class, and the relationship between a trader and the portfolio class is that the trader handles a portfolio, and the customer can be a client of the portfolio. And the portfolio is built up out of instruments and particular stocks. You get the idea. These are classes, and each class is specified by a name, some methods or operations, and so on. So, kicking on to the next one. So here I've got another class diagram, and I got I think 0 all the way up to 1, either 0 or 1 authors classes which have a specific name and particular age, uses a computer, and maybe it's one and the same computer, and the computer's got a name and got a certain size of memory. So a particular instance of this is that CK is a specific object called Chris, age around about 30, and he's got 2 computers because this class is related to this class between 1 and infinity. I mean, any one of these authors could have any number of different computers. Chris Kembock has got 2. So this is the name of the computer, it's a work PC, and CK's home computer, and various statistics. So I can actually exhibit a relationship between these classes, and entirely possible later on that these classes will enable the system designer to implement some behavior relating to a use case. I mean, use case being that an author can actually use a particular computer to perform a particular job. Right? So, 4th type of diagram, which I've actually mentioned several times before in the course, and to which I attach enormous importance, are state diagrams. So such a diagram usually complements a class diagram. In other words, class diagram is actually going to explain the operation, the behavior of a class, how it can be used. In a state diagram, all possible states of a class are shown, and which events cause the state of the class to change. And I'm thinking, a very, very silly example is I've got some kind of air defense system, and it can be in a huge number of states, in the sense that maybe state number 1 is that it's actually monitoring different sectors of the visible sky, and the monitoring activity of all those different sectors involve looking out for a moving object and then change a state in order to calculate the direction of the travelling object and its speed, and possibly later on, given all the information, it's going to try and identify the projectile to see whether or not it's a friend or foe, or whether it's an airline, or whether it's an incoming Scud missile or whatever. So a state change is called a state transition, and a transition may have an action associated with it. So you very often need to provide a state diagram for a complex class, because it's not going to be obvious what this class is capable of doing, what its possible behaviors are. Okay, so here's a little state diagram for a lift. Can you see this? I hope you can. Hope you're still there, Mohammed. Right.
Yeah, I can see it.
I'm pleased to hear you. I thought you'd definitely left the session, but never mind.
The thing is, I'm mute my microphone.
Okay,
So
no.
Yeah.
No, I've got full confidence that you're gonna spend another hour with me, all right? Because we're going to move on soon, and it becomes slightly more interesting. So this is a different kind of diagram. It's called a state diagram. These objects here, these little rounded rectangles, are states, represent different states. These arrows represent state transitions caused by whatever event is marked alongside the arrow. So we start off, the lift starts off on the first floor, and the instruction comes in that it's got to go up to floor number 55, going up. So it moves into a second state where the lift itself is moving upwards. And I'm not quite sure. This looks ridiculous, really, but it moves up. I guess it stops moving up. When it arrives at the destination floor. So this, I don't understand where I've actually got this from. So I should have I should have an arc moving from moving up back to moving up. But if I've arrived at the floor, I do that. I don't do that. If I haven't arrived at the floor, I keep moving up. I've got to go to floor 150. I'm on floor 1. So I keep moving up. But when I get there, when I've arrived at the floor, so this link should actually be arrive at floor. I become idle. I'm just in an idle state. But I might get a message to say, moving down. Oh, I don't know what I'm doing here. Moving down. Maybe I'm changing state because I'm going down. Maybe I get a message, say just move down. I change state to state moving down. I mean, I could say this state diagram itself is a gross simplification of the operation of a lift. And I've got another state machine diagram for a lift that I'll show you a bit later on. So if I'm idle and I don't get any requests for moving up or moving down, I'm going to simply move to the first floor. I mean, maybe I'm idle for a period of 5 minutes. If I've been waiting for a lift request for 5 minutes, what I'm going to do is simply move back to the first floor. And in this state, I'm on first floor. So, okay, I'm going to perhaps. This is a little bit of an explanation of some of the different states that a lift can be in. Not very informative, but it gives you the idea. Here's a much better one. Can you see that? So I've got a state called lift event loop. And if a button's, I'm finding this pretty tricky to read. So if I just make that a bit. So, well, it's in the wrong position. So, how do I move it? So if a button's pushed, I'm going to change state to process the request. And how do I do that? Because I'm thinking about someone in the lift being pressed the button, I think. Turn the button, so press the button on, so that the person in the lift, when he or she sees the button unlit, knows that they've arrived. And I'm going to update the request. I'm going to put the request into the system. And I go back into lift event loop. And I'm going to, other things being equal, depending on whether a button is pressed below where the lift is, or whether a lift button is pressed for a floor above me, I'm going to follow a particular status followed. So here, lift is moving in the direction of D, going downwards and going towards floor 1, and determine next if stop. The next floor has been stopped, so I better check all the registers. Has anyone summoned me to stop on floor X? If no request to stop at floor whatever it is has been received, I can continue to move and move lift just one floor in the right direction, and then I go back up here, and I'm going to continue to move in the downward direction towards floor G. And I keep checking, then I can sort of loop up here and to repeat the action. So I can't actually see all the detail. I'd have to blow it up, and I can't move. I can't expand it because but I'm doing things like if you've got a request, close the lift doors. And you should open the lift doors at some point to let somebody get in if the lift has been requested to stop at that floor. And if the light goes off and you've reached the floor that's been requested by someone in the lift, you should open the doors, wait for a period of time, and close the doors, and then check to see whether there's any other request. If there isn't, you enter the idle state and you rest, you don't do anything. So at first sight, sorry about that. But at first sight, this looks a bit more complicated than the last state machine I showed you for a lift system. So the next kind of diagram, and again it represents a particular view of the system in terms of its behaviour, are sequence diagrams. And what sequence diagrams actually show is the dynamic collaboration between a number of objects. So as you can see, I've got a computer object, I've got a printer server object, I've got a printer, and I've got a queue. So the computer might well send a message to this object that is called print file. And there are two possibilities. The printer's free, so the printer server sends a message to the printer and the print job starts. Otherwise, the computer's asked a printer server to do a particular job. Maybe it's busy. Now what's going to happen is that the printer is going to be queued up, and presumably the printer will actually communicate to the printer server at some point that it's free, in which case the again I don't really the printer server is actually going to send or collect the job on the printer queue and send it to the printer, and the job's going to be finished. And at the end of all that, the printer's actually going to say something to the effect that the job's been done. So what a sequence does, it's not a brilliant example, but it's sufficient. You've got 4 objects, and guess what? They talk to one another. I've spoken in terms of the computer sending a message to the printer driver. What actually happens is that the computer will actually execute a method in the printer queue. And the printer server, when it's received the job, will actually execute a method in the printer class or printer object. I'm going to say, look, print the file called Chris Kenberg, and other things being equal, it'll finish at some point here, or whenever. So I'm a bit confused here. Right. So time is represented by the vertical axis. So these are events taking place in time. And the diagram shows the exchange of messages. Okay, we're talking in terms of diagrams showing how particular aspects of the functionality are implemented. Sequence diagram takes us a little bit further in the right direction. It's saying how these 4 objects collaborate, in a sense, to produce the desired collaboration. So I've got specifically in Mark 6 collaboration diagrams, and I'll show you what those look like in a second. The sequence diagrams essentially do show message passing, communication between objects. And as a result of their communication, there's an indication of how the particular functionality of printing a file is achieved. So hopefully that's reasonably straightforward. So collaboration diagrams show dynamic collaboration, just like sequence diagrams. But often the choice is between showing collaboration as either a sequence diagram or as a collaboration diagram. I think I'm right in saying that collaboration diagrams and sequence diagrams are logically equivalent, in the sense both show how objects actually get together, communicate or collaborate to bring about desired functionality. But the latter show message exchanges, interaction, and objects and their relationship. If time or sequence is important, it's important to use a sequence diagram. So collaboration diagrams are drawn as object diagrams along with their relationships. Message arrows are drawn between objects to show the flow of messages, and messages are labelled with the order in which the messages are sent. Message label can also show other things such as conditions, return values, and so on. So here's Chris Kenberg, this little stick man here, and he pushes a button, and the button communicates. Look, there's number 1. The message is going to be sent to the lift controller that I want the lift to come to the floor that I'm waiting on. What the lift controller does, so this is step 1, 2, is to package the request into some kind of object, order object, which is going to be sent, or the message is going to be sent like, look, there's someone waiting at floor X to the queue. First in, first out. Is that first in, first out the queue? Some kind of data structure here. So the lift's going to be put on the queue. It's going to be put on the end of the queue, isn't it? Chris Kinberg is the 20th of 20 people standing waiting for lifts. And at the front end of the queue is going to be the person that's waited the longest. So we've got a queue of jobs. Now it's being done. The request is being queued up. The lift, however, is going to interrogate the queue object to see what, if any, the latest, the first job that was put on the queue, the one that's been waiting the longest has been, and it's going to service it. It'll respond by going to floor whatever it is that Chris Kinberg's standing. So sorry, just to make this absolutely clear, what a collaboration diagram is indicating is a set of objects, including a button, queue, a lift controller and a lift in the order, and it's each object's communicating with another. And such a diagram is supposed to show how the lift receives a request. I mean, the order might be quite complicated. It might be, he's on floor 40 and he wants to go down. Or another user of the system might press another button and I want to go up to floor 500. And the lift is actually going to take the next job from the queue. And the question might be, is it a priority queue? What's going on here? Is this queue actually sorted out according to... Do you remember in term 1 we looked at something called the C algorithm, the lift algorithm? Maybe you don't, but anyway, that's the collaboration diagram. Seventhly, activity diagrams show a sequential flow of activity, typically used to show or describe the activities performed in an operation. Action states containing a description of an activity did before. Let's have a look at what an activity diagram actually looks like. And activity is making a decision whether a disk is full or there's some free space. If the disk is full, display a message saying the disk is full and end. If there's some free space, tell the user that you're printing whatever it is, a little bit more processing than end. So that's called an activity diagram. So you've got activities in boxes, but it represents sequential flow through particular collection of objects. Right, so if a project that you're ever involved in, if you are ever involved in a software project, contains any element of design, you must address issues of design methodology. I mean, it's no good just sort of trotting out all your code after 7 months of work without any explanation or structure. You must use some kind of design methodology as well as analysis. How have you analysed the problem? Right. So important. Is it enough to say adopting a top-down approach? What does that mean precisely? Justify what you're doing at every stage. Hello, Gemma. Right, so bear with me. We'll just have a couple of minutes of break. I look for something. Bear with me. Right, hi guys. How come no one's showing their webcams again?
I don't know, sir. What's the point?
What's the point? I want to see you. That's the point. And it's proof that you're actually still there as well.
Yeah.
Go on, let me see where you are. Okay, that's me. And I'm going to move on a little bit. I want to move on to this. It's a little case study. We'll try and put all the things that we've been talking about so far together. So I'm going to begin a case study. And I want you to focus on some features of the use cases. So we know that object-oriented analysis is a semi-formal specification technique related to the object-oriented paradigm. So we're looking at analysis, object-oriented analysis. It consists of 3 steps. And the first step is, as we've seen earlier, use case modeling. And this step determines how the results are computed by the product under analysis. In other words, what the system that you're modeling does, what performance you expect, what functionality is to provide. And we don't necessarily want to refer to sequencing of operations. And simply, but importantly, you should think of this step, or these steps, as showing what the system does. And this information is presented in the form of use case diagrams and associated scenarios. So what is a scenario? A scenario should accompany each use case diagram, and it's an instance of a use case. And a use case is supposed to be a typical representative use of the system. This step involving functional modeling is largely action-oriented. You know, if you press the button, you're going to get this result. If you press the button 3 times, this is the different result you're going to get. Something along those lines. The emphasis is on the interaction you, the user or the agent, has with a software system, or a hardware system, or a business system. But secondly, as we've seen, so I'm actually summarizing what we're doing here, class modeling. This step determines those classes and their attributes that are going to be used in the system to bring about the functionality specified by a use case, a use case or multiple use cases. And the interrelationships between classes can then be determined. And the diagram is called a class diagram, as we've seen. And overall, this step is data-oriented. It's to do with data, nothing else. Dynamic modeling, this step determines the actions performed by or to each class or subclass. I mean, some classes do need to be accompanied, to be supplemented by a way of dynamically modeling what that class does. Whoops. Go back to that. What? This is the beginnings of a reasonable case study. And all the steps I've mentioned above are illustrated in our first case study. So this is it. A product is to be installed to control n elevators in a building with m floors. And the problem is to determine the logic required to move lifts between floors according to the following constraints. Right? Each elevator or lift has an integral set of m buttons used to indicate to which floor a lift client is traveling to, and this becomes illuminated when pressed and causes the lifts to visit the corresponding floor, and the illumination is cancelled when the corresponding floor is visited by the lift. And each floor, except the first and the top floor, has two buttons used to request an uplift or downlift. These buttons also illuminate when pressed, and the illumination is cancelled when a lift visits the floor and then moves in the requisite direction. And when a lift has no pending requests, it remains at its current floor with its doors closed. Okay, so what about a little bit of use case modelling? And remember that a use case describes the functionality of the product, i.e. what the system does, and provides a generic description of the system's overall functionality. Be accompanied by scenarios which are particular instances of the use case and represents particular interactions between actors and specific objects. So a UML representation of the use case for our case study appears below. It's not terribly complex, and indeed it shouldn't be. I mean, we've simplified things as far as possible, remember. The only interactions possible between a lift and a user is that a user presses a lift button in order to direct a lift, or a user pressing a floor button to indicate a destination floor. And within this generic description, there is a huge multiplicity of possible scenarios, mostly normal, but some abnormal. Let's have a think about that. And there you go. There's the lift. And the user can do one of two things. He can press the lift button, or he can press a floor button to summon a lift. Okay? So very simple. It's a use case for the lift, one agent, couple of users. It's the only thing you can do with the lift, really. You can press a button. I mean, technically, you can get into the lift when the lift doors open, and when you're in the lift, you can press a button, and maybe if you're in a Swedish lift, you can press. Oh, you can actually verbally ask for the news of the day, and you'll be told. Or you can ask for advice, and so on. That's a bit more sophisticated. So let's run through a typical normal scenario. Firstly, user Chris presses the up floor button on level 3 to request lift. Chris wishes to go to level 7. The up floor button now becomes illuminated. The lift arrives eventually at level 3. It contains a lady called Illuminator who has entered the lift at floor 1 and has pressed the lift button for floor 150. The up floor button is now turned off. The lift doors open. Chris enters the lift. Chris doesn't enter it twice, sorry about that. Chris presses the lift button for level 7. The lift doors close and the lift travels to level 7, and the level 7 lift button is turned off and the lift doors open to allow Chris to leave the lift. Timer starts, Chris leaves, and the lift doors then close after the timeout period. and lift goes to level 150 carrying a luminator. Well, it's fairly detailed, but this is a representation of a typical use of the lift. Okay, a typical use of how I actually interact with the lift. And here's an abnormal scenario. User Chris presses the up floor button and on level 3 to request a lift. Chris wishes to go to level 1. The up floor button becomes illuminated. A lift arrives eventually at level 3. It contains a illuminator who has entered the lift at floor 1 and presses the lift button for floor 150. The up floor button is now turned off. The lift doors open. Chris enters the lift. Chris presses the lift button for level 1. Level 1 lift button is turned on. Lift doors close after timeout period. The lift travels to level 150. Level 150 lift button is turned off. The lift doors open to allow Illuminator to leave the lift. Timer starts, Illuminator leaves. The lift doors close after a timeout period. And the lift goes all the way down to level 1 with Chris on board. Well, that's an abnormal use of the lift. And the point of scenarios is that it gives you, or should give you, enough detail to give the analyst insight into the total behavior of the system being modeled. And the information gained from writing scenarios is that the information is used in the next step or phase, class modeling, by helping to determining the classes and objects that are sufficient to model or implement the system as a whole. And the information will additionally be used in object-oriented design when it comes to verifying the system that you constructed. Does it respect the scenarios? Does it give me the behavior expected? Right. So class modeling, in this phase, classes and their attributes are extracted. Only attributes are determined, not the methods. So in other words, all the variables, the state of each class should be determined, but not the operations you can perform or operations that the class is to perform. The latter will occur during the object-oriented design phase. But following these steps is not a particularly easy task, but the use of objects is rewarding. So, key question is, how are you, the developer, how are you to choose the classes fit for purpose? Well, you can examine the scenarios of both sorts, and a quick look at the two scenarios above, Muhammad and Jumar, is that there is mention of lift buttons and floor buttons and doors and timers. And in other words, I'm just sort of picking out some objects, because they are playing a significant role in each scenario. And these objects determine a typical use of the system. So, believe it or not, there's something called the method of noun extraction, which realistically, I'm not sure whether it's actually religiously followed or whether it's actually used seriously, but it does actually give you some guidance as to how to choose the objects or classes for your system. And for those without domain experience, for example, I don't know whether Mohammed has actually got the experience of spacecraft. If you haven't, then maybe this is a method that you might wish to choose in the circumstances.
Yeah.
First of all, you state the problem definition concisely, specify the product as briefly as possible, preferably within a single sentence. And maybe this will ensure that you, the designer, do properly understand the problem. And here is an attempt to summarize the system and its operation. Buttons and lifts, and on each floor level, control the position of n lifts in a building with m floors. Right? I mean, if you think about it, lift buttons do actually eventually cause the lift to move in all the ways in which it moves. In other words, it controls the position of these n lifts in a building with exactly m floors. Stage 2, informal strategy. Take into consideration the given constraints. There are 3 constraints as far as I can see. Buttons and lifts, and at each level control the position of n lifts in a building with m floors. Just repeating myself, really. But buttons light up when pressed, because that's quite an important function. Unless you want the same button being repeatedly pressed by Z lift clients. Buttons light up when pressed to requesting the lift to stop at a given floor. Buttons light up when pressed and when requesting a lift to stop at a particular floor. Okay, that's right. This is cancelled when the request is satisfied. When a lift has no request, it remains in the current level. So I'm just giving a tiny bit more detail, sort of functional detail, I guess. Stage 3, formal strategy. Identify the nouns in the informal strategy, including those that don't form parts of the problem itself. I mean, what on earth am I talking about? If you give a description of something, there are going to be nouns, and nouns invariably and typically refer to objects. So collect all those objects. Underline the nouns in the informal strategy. So here it goes. Buttons underlined in lifts, and at each level control the position of n lifts in a building with m floors. Buttons light up when pressed to request the lift to stop at a given level, etc., etc., etc. Well, I get 8 different nouns. Button, lift, level, position, building, request, door, can all be provisionally extracted. But buildings, doors and levels lie a bit outside the scope of the system, the main system problem domain. I mean, position and request and illumination are abstract nouns, and it's unlikely they're good candidates for classes, but are better seen as attributes. I mean, maybe what I mean by that is that maybe it's a good idea to think of illumination as a variable in one of the classes, which is can have one of 2 values, on or off, or true or false, or something in those terms. So you're going to have to think a little bit about all that. Why do I say that? I mean, buildings and doors I've mentioned, and one of the things I do is to open and close the door after a timeout period. But we'll think about that. This leaves just two candidates: elevator, the lift itself, and the button. And there are 2 types of button, aren't there? I mean, we've discovered that there are a lift button and a floor button. And what I'm doing here is to say that there's a generic or a class called button, and lift button is actually a subclass of button. A floor button is a specific kind of generic button, and it's a subclass. So I've got, there are M lift buttons. These are buttons inside the lift, each representing a different one of the n floors. And there are two n-2 floor buttons, because the floor button at the top of the lift shaft is just one button, and the floor button at the first floor has just got one button. Yeah, and it's up. But it's a request for the lift to go up from that particular floor. So and here's the lift, and I've just got one variable at the moment. Door open, it's a boolean, true or false. And the lift button is going to communicate with the lift. The floor button are going to communicate with the lift. So I'm actually establishing a relationship between these, there's three, in effect there are going to be three objects: lift buttons, floor buttons, and lift, and an abstract class here. So there are two base classes, lift and button, and the arrow indicates the subclasses of button. Fine. But it's not a particularly good start, because let me see if I can magnify this. Because one of the things I've obviously missed out. So I've got another diagram here. Got a button, a lift button, a floor button, and the door. So I'm going to have doors here, and I'm going to put in an elevator controller. Right. So let's clear this bit. So this is the lift, and it's going to be controlled by the controller. The controller is actually going to control the elevator door. So I've got a new class here, elevator doors, and I've got buttons here, floor buttons here, and the elevator controller is actually going to listen to and be controlled by the controller. I mean, remember, if I press a button, I want the button to tell the elevator controller that there's a client, there's a request on its way for the button for the lift to go up. Sorry, it's for the lift to be summoned, right? And when the lift arrives at the floor that the button was pressed, it's going to turn the light off. And similarly, the floor button's going to be pressed inside the lift to express the desire of people in the lift's destination floors. And when I arrive at the particular floor, I'm going to turn the light off. And when when the controller senses that I've arrived at a required floor, I'm going to open the doors, wait X seconds for the person waiting for the lift to get in, then the controller is going to actually tell the lift doors to close. So to me that all makes reasonable sense. Yeah? Hopefully. Okay, well I'm going to close this down. Mohammed, I still can't see your webcam. Jumar is listening, but he's not showing me his web camera.
Showing you a thumbs up, isn't that enough?
I want to see what you look like. You might be wearing a funny hat, or might be asleep, or you might be in a dark room, or whatever. Right, I'm going to take a 5-minute break. Yeah? So I'm just going to, I should play some music for you, but I haven't got the facility at the moment, so just bear with me for 5 minutes. to talk a little bit about lift systems and request queues and how we can actually construct a queue. And last week, I'm sure you were delighted to look at the YouTube video on how to make a linked list. And hopefully you've got some idea of what a linked list is now. I want you to come to understand the logic of placing something on a queue and removing an item from a queue, given that we intend at some point to implement a router queue or packet buffer on a linked list. Or in the instant case, I want to be able to queue requests coming in from floor buttons and lift buttons. Right, so my question is, how can a buffer be implemented? Is it first in, first out? Could you use a linked list as a queue or as a dynamic buffer? And by dynamic buffer, I mean maybe one thread can take something from the queue, and at the same time, another method can put something on the queue or the buffer. Now, the question I'm asking you to think about is, what's the simplest way that you could implement a queue or a buffer? Would you use a region of memory? Would you use a circular array? And if you don't know what a circular array is, can you check that out? A little 5-minute exercise on the internet. Would you use an array or what? So, if a process is putting data in and another taking data out, I should say, how is this to be managed? And what I'm going to do is to just talk about linked lists as a way of implementing a queue, and I want to build a class queue in this way. It's going to consist of elements, that's just the one I've shown you here. So it's going to have so this is going to be of type element, and it's going to have two fields, two variables. One is of type element, and I'm going to use that to point to or to name the next element on the queue. And maybe I've got some data, I'm not sure. I'll leave that open at the moment. So I'm choosing element to be very general here. And the convention I'm going to adopt is I'm going to let an element called head point to or index the first element. And I'm going to let an element called tail point to or name or index the last element in the list. So in other words, if tail points to the empty node, the empty object, and the head points to the empty object, the list is empty. So here's a representation of the empty queue. Head refers, his next element is this here. Tail typically is used to represent the end of the linked list. It's going to have null as the next element. Null represents the null element, nothing. There isn't one. So let me show you a non-empty queue containing two elements. Head is actually going to point to the first element on the list, called element 1, an element. Head is an element. The variable next is of type element, and it's going to name element 1. And element 1 has a field called next, and it's going to point to the second element, element 2. Here it is. And the next field in element 2 is going to point to the null element. And this signifies this, the importance of this null object is that it represents the, it means that this is the last element in the list. This is the first, this is the second and last. And tail actually points to or names the second element. This is the end of the list. So, so what I'm going to do is to demonstrate pictorially the append operation, because I can do two things to a list and a linked list. I can append something to the beginning of the list, and I can remove something from the end of the list. So have a look at this. I want to append an object. I want to append this object to the list. So what do I do? Logically, what I need to do is to make head's next field point to this element, to this new element that I'm adding on to the beginning of the list. And I'm going to make the next field of this new object, in other words, it's the first object on the list, point to the old element 1. So this link, this pointer disappears, this arrow goes, right? So I've just got this arrow here, then an arrow from next to this element. And next refers to element 2 as before, and the next, so-called next, the fictional next element of element 2 is the null object. So, if I want to get the last element on the list, what I need to do is to simply cut this connection, and cut this arrow, and make element 1's next field point to null. That indicates the end of the list. This element is the end of the list because it points to the null object. And I'm going to make tail point to the list up to the last element of the list up to the element that I've just removed. I'm removing. I'm going to take this away. Okay. So the logic of lists is that if I put X onto a list and there's nothing on the list, X is going to be picked for whatever is in store for it, first of all. If X is put on a list and then I append Y, I've got two elements, and if I remove element X, then Y is going to be the next element to be serviced or to be chosen from the list. Okay, so you can think of people queuing up for a bus. I'm first in the queue, 10 other people, and 10th person is the end of the queue. And for each person, I'm going to append them to the queue, logically append them to the queue. And first element, and logically the first element of the queue is going to be the last element, the element pointed by tab. This has been waiting on the queue for the longest. When I take it off, this fellow gets to go on the bus. His turn next, his turn next. I can append another 9 elements prior to the object that I most recently appended, and I'm going to make head point to the very last element I appended. So that looks reasonable, if only I knew how to do this in Java. So I'm going to give you a bit of code, develop a little bit of code, and then give you a little demonstration. What I needed to think about the safety properties, cannot, shouldn't be allowed to get an object from the middle of a queue. Ridiculous. It's like jumping the queue. Append only to the front of the queue. Take an object from the queue, take the next person to get on the bus from the back of the queue. So the last element of the queue. That seems fine. It'll work. It'll do the job. But what you need to know in the following discussion is that if code is marked as synchronized, at most one method within the synchronized block can be executed per window of time. So, for example, a method can execute a wait operation that effectively suspends it, enabling another method to execute. When the latter is finished, it can execute a notify operation that wakes up the suspended process or thread. So why is this relevant to the development of the queue? Well, this is why. Supposing two different methods attempted to remove one and the same element from the end of the queue. I mean, who's to say what'll happen? I mean, the consequences could be bad. Maybe I'm using the same data twice to do some kind of computation, and that would be either dangerous or ridiculous. Another example, supposing at the same time that a thread is attempting to put an object, to put an element onto an empty queue, another thread attempts to remove it. So as you put something on the queue, I'm about to take it off. That's really bad news. I mean, it could crash the system, perhaps. Very dangerous. So what I'm actually saying by talking about this is that I can get a lock on some code in such a way that if I want to do an operation, I'm going to exclude you from doing an operation at the same time. And if I've got a lock on some code or a method or whatever it is, if I've got the lock on it, I'm going to force you to wait. So you can execute a wait statement. You're just waiting for the lock to be removed before you execute the method that you want to execute. And I, who have got the lock on a method or a block of code, can actually release the lock by simply executing a notify statement, a notify operation, because that's going to wake you up, and you'll be in a situation where the lock's been removed, and you can go ahead and do the operation that would otherwise have been very dangerous. So here, I'm building a queue in Java, and it's got all the features I've been talking about, I reckon. So here's the class queue, and head and tail are both type element, and here I'm marking a method called append as being synchronized, and if tail is null, the queue is empty, and I can make E, which I want to append, to be the first element. So I simply set head to be E. Otherwise, I'm going to execute these 3 lines, which has the effect of appending, according, I think, to the diagram I've just shown you. That'll actually add E on to the existing list. And I finished the business. I've done, by this point in the method, and I've actually finished adding E onto the beginning of the list. And I'm going to execute this notify all statement. It could be notify, but I'm choosing to use notify all. And what this does is to let the lift know. No, forget about it. Let it know that. Oh, forget about this. I'm going to do 2 things. I'm going to let the lift object know that something's happened, that there's another job on the queue. And secondly, I'm going to, this notify all allows any other thread that wants to execute get take something from the queue, which is great because I've got you can't. What I'm saying is that you can't safely execute append and get at the same time. I mean, maybe 3 threads want to take something from the queue. I'm not going to allow that to happen. So I mark a get method as being synchronized. At most, one thread can actually execute get, and similarly with the append operation. And the little message here, which is to notify, any other thread that wants to use one of the synchronized methods, that it can now do so safely. And that might include the lift method, who wants to see if there's more work to be done on this queue that's being put on this queue. A little bit more code here, and a little note here. So, but you're going to have to think. You're going to have to think about the situation where, if it's, and this is important, and this might form part of an exam question. It's like, is it safe for one thread to do a get and another thread to do an append if the queue has got at least one element? Supposing I'm about to append an element E onto a list that has got just one element, J. Is it safe for one thread to get J at exactly the same time that another thread appends E? And it seems to me as though that's quite safe, providing that the condition is true, namely the condition that the list is not empty. So will you think about that? And I want you to let's go back for a second. Just go back to this note here using notify. I'm going to let the lift itself know that a task has arrived. The job description has been right. Because it might have been waiting until there's a job on the queue. Okay? Maybe the lift has been waiting to execute get, but it's being forced to wait because the queue is empty. There's nothing in the queue. It's got to wait. But if I come along and append something, the get method will succeed in removing a job from the queue. Here it is. Okay. So let's have a little gentle think about that. And it reflects the discussion we had 2 weeks ago on semaphores. You know, the non-shareability of lots of resources. And I want you to think about the shareability or non-shareability of a list. And the reason that we have to be bothered by it is because a lift might be represented by a thread. And we might actually have 2 lifts, or M lifts, and there are possibly hundreds of buttons that are appending jobs onto the queue. Okay? So let me see. I think that's all I've got here. Talk to you about other than I'd quite like to just share my screen if I can. I've got an application. No, I haven't. So I'm just going to set that up, so bear with me for 1 minute. So I'm not being given permission to share my window. I'm going to pause recording for a minute. Okay, so hopefully you're watching an Eclipse shared window, and the program I've got is lift. So I've got a class called element, and so here's the main class lift. And guess what? I'm going to implement runnable. In other words, I'm going to run it concurrently with two other threads. So I've got another thread, and it's formed by using the class controller. Implements the runnable class, and one of the things that the controller is how I'm doing it. I'm putting a task represented by an integer between 1 and 100, a random integer between 1 and 100 on the queue. This is the view class. And my class nog, for some reason called it nog, it involves 1, 2, 3, 4 threads. And a bit of code right at the beginning that generates a random number. It's not the ideal way of doing that. Here's my class element, class CKQ. Is actually the code that I've already shown you. So you can check that out a little bit, see what's going on. And the key thing is that this program, public class nog, public static void main, is actually starting lots of threads, and therefore it's a concurrent program. I've got a lift, a couple of lifts, 3 lifts in fact, and a controller, and the lift itself all running in parallel. I'm going to run this, and it's not terribly exciting to look at, but and it indicates that each line indicates a lift going to a particular floor. So lift 2 is going to floor 17, lift 1 is going to floor 17, lift 2 is then going to floor 12, and so on. So yet another example of a concurrent program, and it's a sort of very, very simple implementation of some of the ideas that we've been looking at in the UML case study. So see if I can get back to safety. Here we are. So you have a 132-minute recording. I'm sure it's of variable quality because you're not here to interact with. Juma, are you still there? You appear to be connected. But there's no webcam. There's no webcam and no response to my questions. Oh, you are there, because I was fasting today. I'm so sorry. I'm eating. Eating and fasting.